Okay, here we're starting video K. This is question 11A from your workbook. And just note that video J was a YouTube video about bomb calorimetry. In case it didn't download as part of the movie that you watch for this part 4 lecture, I'm going to post that link to that video for you, because it is something I'd like for you to watch, and it'll help you understand this question. I understand that this is blurry. This is the best that this camera can do, but you should have a copy of this in front of you. So the question's asking about a sample of benzoic acid, which is C7H6O2. And sometimes people will take a sample of solid benzoic acid, put it in their bomb calorimeter, go ahead and add oxygen and a spark, set it off, it produces heat, and then the heat is transferred out of the bomb. Now, this is often done with benzoic acid because it can be obtained in highly pure form, and so you don't have to worry about impurities, and it doesn't absorb water and things like that. So it's a way of combusting something that's reliably pure and easy to weigh. So in this example, we have a 1.221 gram sample of benzoic acid, and it's combusted in a bomb calorimeter. Now you can go ahead and write that combustion reaction by combining this with oxygen and making carbon dioxide and water, but we actually don't need to do that for this question. So remember that with calorimetry, we often have heat leaving one place and going to another place. In this example, the heat from the reaction is the system. And so heat is, because it's highly exothermic, heat is produced in the reaction, and so the reaction is going to give off heat, and that's coming from the bomb, and that heat is going to go, in this case, to two different places. It goes into your water, and it also goes into your calorimeter. The calorimeter does absorb some of the heat from the water because they're in contact with each other. Now, you might be wondering, well, maybe you did a coffee cup calorimetry experiment once and you didn't really worry about this. When we do coffee cup calorimetry, it's much more casual, and we don't often include Q calorimetry, or Q calorimeter, I meant. So in this case, we argue that because bomb calorimetry is used for very precise measurements. Okay, so what we'd like to do is we'd like to add Q from the calorimeter to Q from the water. And we can figure both of these out using the regular Q expression that we've been seeing for all of our calorimetry. Q equals mass times heat capacity times delta T. Now we're given the heat capacity of the calorimeter itself. So that is equal to 1365 joules per degree Celsius. Now you might be wondering, well, wait a minute, why doesn't that have a mass on the bottom? Often for calorimeters, you'll just see units of joules per degree, and that applies to the whole mass of the calorimeter. And so in order to find Q, instead of multiplying it by the mass of the calorimeter, which would be difficult to figure out, somebody already included that in this number. So all we have to do is multiply this by the change in temperature. So in this case, we're going to say Q is equal to C calorimeter times delta T. So let's go ahead and do that first. So delta T times C calorimeter. Delta T in this case, if we subtract the two temperatures, we get 5.053 degrees Celsius times 1365 joules per degree Celsius, and that gives us 6897 joules. That is the amount of heat absorbed by the calorimeter. Then we have Q of water, and that is going to be done the way we always do it. We're going to take the mass, 1.200 kilograms, and we're going to multiply by the heat capacity of water, which you would have to look up. Okay, and then we're going to multiply by 5.053 degrees. Okay, and what do you notice here that's going to be a problem? Well, I'm just going to put a 1 here on the bottom. You might notice that we have kilograms and grams, so we need to multiply by 1,000 grams over 1 kilogram. Okay, and then that gives us 2.53 times 10 to the 4th joules. So you can see the lion's share of the heat is going into the water, and a small amount of the heat is going into the calorimeter. So let's go ahead and add those together. So negative Q reaction is going to equal 6897 joules plus 2.53 times 10 to the 4th joules, and that gives us 3.22 times 10 to the 4th joules. So therefore Q reaction equals negative 3.22 times 10 to the 4th joules. Now we're often working in kilojoules because we have these large numbers of joules, so I'm going to convert that. Oops, sorry about that. I'm going to convert that to kilojoules, and that's going to give me negative 32.2 kilojoules. So that is the heat given off by the reaction. Now, as we discussed in class, this differs from delta H because delta H is going to have a denominator that has an amount of substance. Okay, so in this case, we have, let's see, delta H equals negative 32.2 kilojoules of heat is given off by 1.221 grams of benzoic acid. Now we need the molar mass of benzoic acid, which I calculated to be 122.12 grams in 1 mole. So you have to look that up or calculate it based on the chemical formula that you're given up in the question. Okay, so this gives us negative 3.22 times 10 to the 3rd kilojoules per 1 mole. The reported value, by the way, if you go online and look this up, is negative 3.226. So we're pretty close. Okay, so this is our final answer. That is the enthalpy change for the reaction. So when we did Hess's law and when we did heats of formation, we're looking at all those measured values for delta H. Well, this is how they often are measured, is using bomb calorimetry. And you can see that our values here are close together.